Hello everyone, this is Shahid Afrid and my colleague Jaya Krushna, and we are here today to give a presentation on MLP-GA-RF, hybrid machine learning with fog integration for advanced heart disease prediction. This research project is conducted by Department of Computer Science and Engineering, specialized in data science, at Rajeev Gandhi Memorial College of Engineering and Technology. We are fortunate to be working under the guidance of Dr. Sri Raghavendra Sir, an associate professor in the Department of CSE Data Science. Today, we'll walk you through the core concepts of our project, including the problem statement, objectives, proposed methodology, and key findings. To give you an initial understanding, our project addresses the critical challenge of heart disease prediction, a leading cause of mortality worldwide. We propose a novel hybrid machine learning model, MLP-GA-RF, which uniquely combines a multi-layer perceptron, genetic algorithm, and random forest. A key innovation is the integration of this model with a fog computing framework. This integration allows data to be processed closer to its source, significantly reducing latency and minimizing reliance on centralized cloud infrastructure, making it ideal for critical healthcare applications and remote patient monitoring. The abstract section outlines a research project addressing the critical need for accurate and timely diagnosis of heart disease, which remains a leading cause of mortality worldwide. The study proposes a hybrid machine learning model called MLP-GA-RF. This model combines the strengths of multi-layer perception MLP, genetic algorithm GA, random forest RF. The genetic algorithm is utilized to efficiently optimize the MLP's parameters, thereby enhancing its predictive performance. Random forest RF then acts as a robust classifier for the final diagnosis. To further improve real-time diagnostic capability, the entire system is integrated with a fog computing framework. This decentralized approach processes data closer to its source, which significantly reduces latency and minimizes reliance on cloud infrastructure. This makes system particularly suitable for critical healthcare applications and for remote monitoring. The MLP-GA-RF model is rigorously evaluated against conventional classifiers such as logistic regression, SVM, decision trees, and XGBoost. The evaluation uses metrics including accuracy, precision, recall, F1 score, and AUC. Results consistently demonstrate that enhance accuracy and reliable predictions. In summary, the integration of fog computing with this optimized hybrid model represents a significant advancement in heart disease prediction. Let's begin by understanding the gravity of problem. A heart disease, also known as cardiovascular disease, encompasses various illnesses affecting heart and blood vessels. Cardiovascular diseases are leading cause of mortality globally. According to for over 70% of all deaths, it's estimated that approximately 43% of major deaths are due to cardiovascular diseases. The global economic burden of cardiovascular disease was projected to be approximate USD 3.7 trillion between 2010 and 2050. Worryingly, reports from the World Health Organization WHO indicate that the total number of deaths from CVDs is projected to increase to 23.6 million by 2030. This highlights the urgent need for predictive tools. Our approach leverages machine learning (ML), a powerful branch of artificial intelligence. ML enables computers to learn from data and make predictions or decisions without explicit programming and improve their performance over time, often optimized using techniques like loss functions and gradient descent. Complementing this, we utilize fog computing. This is a new computing model that extends computational capabilities to the edge of the network, allowing data to be consumed and processed more readily. Its architecture is designed to meet increasing demands of real-time data processing, especially for Internet of Things IoT application in healthcare. Coming to the problem statement, as mentioned, heart disease is the leading cause of mortality worldwide, making early and accurate prediction crucial for effective treatment and prevention. Traditional diagnostic methods are often time consuming and require extensive clinical evaluation. While machine learning techniques have shown promise in analyzing complex medical data to improve disease prediction, there's still a need for enhanced accuracy and real-time capability. This project specifically proposes a hybrid multi-layer perceptron MLP generic algorithm GA random forest array model to achieve this. The NLP, a type of neural network, is trained using genetic algorithm for optimization, and the entire model is evaluated publicly available Cleveland heart disease dataset. As mentioned, heart disease is a leading cause of mortality worldwide, making early and accurate prediction crucial for effective treatment and prevention. Traditional diagnostic methods are often time consuming and require extensive clinical evaluation, while machine learning techniques have shown promise in analyzing complex accuracy and real time capability. Coming to the next slide, there are objectives. Firstly, to design and implement a novel model using hybrid machine learning algorithms for heart disease prediction. Secondly, to develop a fog computing framework to enable real-time heart disease prediction. Thirdly, to design and implement the model to achieve robustness and generalization across different datasets. And finally, to rigorously evaluate framework's performance in terms of accuracy, scalability, ensuring its practical utility. Now coming to the existing model. Before delving into our proposed solution, let's briefly look at existing hybrid approach, the MLP-PSO hybrid algorithm, which is also designed for heart disease prediction. Its working process typically involves data pre-processing of datasets like Cleveland heart disease dataset, initialization of population of particles, each representing MLP parameters, fitness evaluation of each particle based on model accuracy and error rate, particle update, where particles adjust positions based on personal and global solution, training the MLP with optimized parameters, and finally, prediction and evaluation using metrics like accuracy, precision, recall, and F1 score. However, this existing model has limitations, including risk of overfitting, slower convergence, and computational complexity, which our proposed model aims to address. Coming to the next slide, it is proposed model. Uh, our proposed model MLP-GA-RF hybrid model integrates three powerful components. Let's break down first two: multi-layer perceptron MLP and genetic algorithm GA. The multi-layer perceptron is a type of artificial neural network. It consists of an input layer for patient data like age, blood pressure, and cholesterol, one or more hidden layers applying for non-linear activation functions, and an output layer for classification. Its primary role is to perform initial classification of heart disease. Coming to the next algorithm, that is genetic algorithm, is used to optimize MLP's model parameters, including its weights and biases. GA mimics natural selection, generating multiple solutions, evolving them over iterations by selecting the best parameters using fitness function, typically based on minimizing classification error and maximizing accuracy. GA ensures the MLP achieves better accuracy and minimizes prediction errors. Now my colleague Jaya Krushna will continue the next slides.
Hello everyone, I am Jaya Krushna. Now I am going to continue our project, Random Forest. Random Forest is an assemble learning method consisting of multiple decision trees. Each tree is trained on a different subset of data. After the MLP is optimized using GA, its predictions are further refined by Random Forest. The final prediction is determined using a majority voting mechanism, which ensures robustness and minimizes model bias. RF is particularly effective in reducing overfitting and improving the reliability of predictions. Real-life applications. RF is widely applied in healthcare, e-commerce, image recognition, and fraud detection. Fog computing integration. Unlike traditional cloud computing, which processes data centrally, fog computing performs data processing closer to the data source. Fog nodes such as local servers or edge devices are deployed to reduce latency, providing real-time diagnostic predictions. This architecture is highly beneficial for remote healthcare applications where immediate diagnosis is crucial for patient treatment. The fog computing layer preprocesses the data, applies the MLP-GA-RF model, and sends predictions to healthcare professionals. This decentralized approach ensures rapid data analysis and minimizes reliance on centralized cloud infrastructure. Now let me explain about the literature review. This study introduces a hybrid machine learning model that integrates multi-layer perception (MLP) with particle swarm optimization (PSO) to enhance heart disease prediction accuracy. PSO is used to optimize the training process of MLP by fine-tuning its parameters, improving model performance. The model was tested against 10 other machine learning algorithms using Cleveland heart disease dataset. Results demonstrated that the MLP PSO model achieved the highest accuracy of 84.61, making it a promising tool for early detection of heart disease. Some of the algorithms used are MLP particle swarm optimization MLP PSO. This study focuses on applying EDA and machine learning to predict heart disease. The research investigates clinical attributes related to heart conditions and evaluates various ML model performances. A hybrid model combining random forest and SVM algorithm was developed, was achieved a remarkable prediction accuracy of 93%, outperforming standalone models. The study utilized a public heart disease dataset available on Kaggle. This paper presents a heart disease prediction framework that uses the enhanced Whale optimization algorithm for selecting significant features. Selected features were passed into classifiers like K nearest neighbor KNN, support vector mission SVM, random forest, and hybrid models such as HSV-RF and HSV-KN. Performance metrics like accuracy, precision, recall, and F1 score were evaluated. The hybrid SVM-RF model performed the best, achieving an accuracy of 85.79. The study used the Framingham heart disease dataset from Kaggle. This research focuses on predicting cardiovascular diseases using multiple machine learning models, with an emphasis of improving accuracy through clustering and hyperparameter tuning. K-modes clustering was applied initially, followed by training several ML models. Grid search CV was used for hyperparameter optimization. The multi-layer perceptron achieved the highest accuracy of 87.28, outperforming other models like random forest, decision tree, and XGBoost. The study utilized a cardiovascular disease dataset from Kaggle. This study developed a heart disease prediction model using particle swarm optimization for selecting key features and logistic regression for classification. The process included data pre-processing techniques like outlier removal and future scaling on the USA heart disease dataset. PSO was employed to identify the most relevant features, reducing dimensionality and improving model performance. The optimized logistic regression model achieved an impressive accuracy of 90.74, surpassing traditional feature and selection techniques. Now, let me explain about methodology and dataset. This slide outlines the structured approach taken to implement and evaluate the proposed model along with the data used. Methodology steps. First one. This involves cleaning, feature selection, and scaling of the data. Second one. Implementing the MLP neural network for classification. The MLP model is trained using the backpropagation algorithm to adjust weights and biases. Nonlinearity is introduced via ReLU and sigmoid activation functions. Step 3. This step involves initialization, fitness evaluation, selection, crossover, and replacement. Step 4. After MLP training with GA, RF is used to refine and improve predictions. RF is trained on the MLP-GA augmented dataset, learning patterns from both original features and MLP-GA results to make the final predictions. Evaluating the model using performance metrics. The model's performance is assessed using metrics such as accuracy, precision, recall, F1 score, and AUC. Step 6. The performance of the MLP-GA-RF model is compared against other models like MLP-PS4, decision trees, k-nearest neighbors, and support vector missions. Dataset use. This study utilized the publicly available Cleveland Heart Disease dataset. This dataset consists of 13 features, one target variable, and 303 instances of patient health indicators. Now, the system design. In this, the data from the IoT devices will undergo two phases. First one, data pre-processing and data splitting. Now, this data is sent to the model that is selected and the data will undergo evaluation. Now, let me explain algorithms use. I already explained about this, so let's understand the applications of the algorithms used. Multi-layer perceptron. Its real-life application include image recognition, natural language processing, and speech recognition. Genetic algorithm. Real-life applications of GA include medicine, engineering, gaming, marketing. Random forest. Its real-life applications are found in healthcare, e-governance, image recognition, and fraud detection. Now, let me explain about the results that we obtained from our project. This slide presents the key findings and quantitative evidence of the proposed model effectiveness. Superior performance of MLP-GA-RF. The MLP-GA-RF model was rigorously evaluated against conventional classifiers like logistic regression, SVM, decision trees, XGBoost, grading boosting, KNN, and MLP-BP. The results consistently demonstrated its superior performance, offering enhanced accuracy and reliable predictions. Specific performance metrics. The MLP-GA-RF model achieved an accuracy of 0.95 and its precision is 0.92, recall 0.92, F1 score 0.94, and AUC 0.949. Now, I will come by comparing with other models. For instance, KNN achieved an accuracy of 0.90 and Random Forest achieved 0.88. Evaluation metrics. Accuracy. The ratio of correctly predicted instances to all instances. It is calculated as ratio of true positives plus false true negatives to the true positives plus true negatives plus false positives plus false negatives. Precision. The ratio of correctly predicted positive instances to the total number of predicted positive instances. Recall. The ratio of correctly predicted positive instances to all instances in the actual positive class. F1 score. The weighted average of precision and recall, providing a balance between the two. The technical requirements. This slide details the necessary software and hardware for the project implementation. Software requirements. Software Anaconda, primary language Python, framework for. Now, hardware requirements. Operating system Windows 11, processor Intel Core i3, RAM 8 GB, and hard disk 25 GB. Finally, we wish to acknowledge the valuable research that informed and supported our work. These are the academic papers and studies that provided foundational knowledge and comparative insights for our project. Thank you for letting us to explain our project.